Okay, question number 3. The diagram shows the path of a ball in the absence of air resistance. Q is the highest point of the ball's trajectory. Okay, A is the vertical acceleration at Q. At impact, the velocity makes an angle theta to the horizontal. Okay, the three statements about the actual motion of the ball when the air resistance are. Okay, the question tells you that in the absence of air resistance, this is the projectile motion. In the presence of air resistance, what happens to the following parameters? Now first let us draw the trajectory to understand what exactly happens. When you say air resistance, how does the air resistance act? Does the air resistance act only like this? No, it does not act like that. Air resistance is nothing but resistance given to the motion of the object, okay, along its full trajectory. When the particle is being launched here, air resistance is like this. When it is at this point, air resistance is like this. At this point, air resistance is like this. Everywhere when you draw a tangent, the opposition is given like this over here. So therefore, at every point it is been acting like this over here. So as a result of this, what can happen is that okay, air resistance acting over here. So when you consider these motions over here, you observe that air resistance will have both an x component and as well as a y component. So because of this x component, definitely this motion has been obstructed. The range is now being reduced, and due to the y component, so the Q value cannot be achieved. So what happens is this particle should undergo something like this. So first thing is the Q value will now come downwards, and this will definitely be an asymmetrical one. Okay, it will be an asymmetrical one because as it keeps on going upwards, the G value and along with the air resistance vertical component, both of them will act downwards. Okay, so the net acceleration downward will be greater than G, and here what happens is when it is going downwards over here, the G value will be acting downwards over here, but since you have a air resistance like this at this point, there will be a vertical component over here, so this will have less than G over, right? The accelerations at these 2 points are totally now different, right? So at every instant it's different. In case of the symmetrical parabola, it is not so. Okay, the accelerations of the particle is always the same. It's pointing downward, the direction is same, and it's also the magnitude is always the same, which is equal to 9.8 or 10. But here it is not so. At every instant it will keep on differing. Okay, now coming back to the question. So what did we learn here? We have learned that the value of Q now reduces. Q is lower. This is right. Then A remains the same. What happens to the value of A? What is A here? A is the acceleration due to gravity at this point, right? See, remember, this is not the net acceleration. See, because I told you here the net acceleration changes. At this point, the value of A, at this point. What is this point here? The peak point over here. At this point, this is the value of A here, which would definitely be equal to 9.8 because the particle's direction is like this. The resistance would be like this, right? So this will not affect this acceleration. So therefore, this value of acceleration should and will remain the same. But if I ask you what will happen to the acceleration at this point and this point, definitely the accelerations are different. Okay, so therefore this is also correct. Theta increases. Now what about this over here? Now when you come over here, now what is happening over here? As it comes down, okay, your Vy, your Vx. Now what is your Vx over here? Vx, okay, let us write Vx at every instant here, everywhere it keeps on reducing over here. Earlier Vx was constant. Here Vx becomes a Qx minus Ax into T over here. So therefore this Ax is now present, it's not 0, so Vx will definitely reduce. If I draw a line here to understand precisely what happens to the theta here is nothing but this is your Vy, this is your Vx, so I can always write tan theta is equal to Vy by Vx, right? When the value of Vx reduces over here, tan theta will increase. When tan theta increases, theta will also increase. As theta increases, so this definitely is a wonderful problem which relates many concepts of projectile motion. Okay, so if you solve this problem, you know or you understand clearly about how to solve such questions, or you get a grip on the projectile motion. Okay, thus the right answer is 1 to 1.